My name is Dr. Shobhu Sachisyan. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bouquet is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, we have added the topics. So the idea is that it is tailor-made for you. It is made for you only. Okay, what is needed? Okay, for you. You know, all these things you are doing because you as a computer science and engineering students or information technology students, when you will be passing out, as per the, because our college is NBA accredited, okay, some of the courses. So as per the requirement of NBA, you know, you're in an outcome-based system. As NBA guidelines suggests, you should be coming out with 12 attributes, which are called program outcomes. Okay. So now those program outcomes you attend through variety of courses. In every semester you have got 5 papers. So at the end of each semester you will be passing actually coming across almost 35 to 40 theoretical papers depending on the course. So there are 2 physics courses. Now these courses are there to attend some of the program outcomes. So our course have got some course objective and obviously some course outcome. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. You know, the entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE and IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and you know, this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. Okay, thank you.
Hello students, how are you? I hope everything is fine at your end. Today we are going to begin our the third class in the series of the studies on quantum mechanics 2. It is the class 3 of the quantum mechanics 2 courses. As I repeatedly mentioned, that in the past 2 classes we mainly concentrated on whatever we discussed in the quantum mechanics 1 course that we studied in the first year classes, where we mainly learned some experiments that was carried out between 1900 to 1927 and today you are with some lesson about the fundamentals of how quantum ideas developed. So if you look into the business, actually how everything cropped up in this way. Okay, two major concepts were shared. One is the wave particle duality, which talks about that a wave may be matter-like, light can be photon-like, and the other concept is the reverse concept. That is the concept of de Broglie, that a matter can electron can show the property of wave. I am not telling opposite is true from the perspective of de Broglie, that a matter can show the feature of wave. That is the what I am talking about is that electron can show the property of the wave. Say in Compton effect, electron makes collision with photons. It is showing the collision is a material property because only matters can collide. On the contrary, in the photoelectric effect, electrons was making collision with the electron. So who collides? Matter collides. So it's another property. Okay, another idea. Actually, most of the things at the back of our mind, we think electron is a matter. With some mass, 9.3 × 10⁻³ kg, which all of you know, with some charge, if electron moves, we get some current. So we think electron is a matter. If you think ohmic way, electron collision gives resistance. If you heat a metal, more resistance. So we have been thinking at the back of our mind, electron is a matter. Okay, but what de Broglie is telling that there will be experiments in nature where the same electron can show the property of the wave. And it was a proposal initially. The concept of de Broglie wavelength was shared with you. And ultimately, within 3 years from de Broglie proposal in 1927, Davison and Jarmer has shown diffraction of electron. Okay, just like they do laser diffraction in first year courses, where red light passes through a glass grating and makes interference, gives you ultimately pattern intensity variation. Similar experience was made with electron being scattered from the atomic plane, and the electron waves were superposing and constructive interference was there. If you could just get back to your memory lane a bit, you will realize it. And what we did there, we measured the wavelength of electron also. So what all this thing is manifesting, this single word, that what it is manifesting, that electron can be wave-like, and its wave property has been confirmed also. Now, and so this is one of the major concepts we need when we progress further in our discussion. And what I did every day onwards, today also, I'll remind you every day that, you know, in our class, our focus will be on this issue. That is, what would happen, how to describe the situation if a matter shows the wave property. Because, you know, 4 things can happen. If you look at your old ideas, 4 possibilities are there in nature. That a matter can show the material property, normal mechanics, two bodies are colliding. And how to tackle that situation, Newton has taught you. Okay, you spend 4 years with Newton for that. And a wave can show the property of wave. The normal experiments of reflection, diffraction, interference, okay, even you studied in first year, you did experiments like Newton's string, etc. All of them are manifesting the wave-like property of the wave. Okay, there is superposition of waves, scattering of wave. So you know this, you studied somewhere else, you spent 4 years in all discussing all these issues from the 10th standard to 12th standard. So now another aspect that I essentially discussed in your first year days, that a wave is showing the property of matter, the photonic property that you already studied from my classes, okay, the photoelectric effect and Compton effect. So, but we are not interested about these issues because this thing you know. What we are focusing on the last issue. We are following the idea of de Broglie. We'll move with de Broglie. That is something that is uncanny to you. You do not know how to describe that situation. You only know, as proved by Davison and Jarmer, electron can be wave-like. So what I tried to do in the last day, so we have focused on this issue, how to tackle this peculiar situation. So first thing that is to be answered in this, and these are the pictures, variety of the waves, wave-like pictures of the electron. So this is something we discussed, okay, that electron can be wave-like. So what is discussed after that, what is spent on telling after that, okay, fine, electron is a wave, okay, electron is making interference in the constructive interference in DVG experiment. But it's a wave of what? As you can see in those wonderful pictures, those, as you, in chemistry courses, in atomic structure problem, you learned it, S wave, P wave, waves of the electron. But is that electron becoming a wave? No, answer is not like that. This is a wave of different kind. It is not like light and sound. So what I actually presented the whole situation in this way. I ask you, okay, fine, you see something is changing, something is varying, so something is waving, I should say. But what is that something? So to answer that question, we actually ask the basic question of the wave theory. How a wave is made of? Wave means disturbance, wave means fluctuation, okay, wave means variation. Okay, any disturbance, any variation, any fluctuation is basically it makes a wave. It may be ordinary. Okay, these are so many examples I have given you. Okay, you can see here. And the popular wave may be light and sound. Sound wave is the vibration of the material particle making the body. So this is called mechanical wave or elastic wave, which I illustrated lastly also. And the other part of the story is the electromagnetic wave, which is a vibration of electric field and magnetic field. What I again try to tell you, therefore, to make any wave, something has to vary. Maybe the displacement of something, displacement is a physically very measurable quantity. So it's something meaningful, physically meaningful entity is varying. Say electric field and magnetic field, they together are making the electromagnetic wave. Electric field and magnetic field is also physically meaningful. I hope everybody knows it, that anything is, in physics, we say anything is physically meaningful, which is measurable. You can measure distance with a meter scale. You can measure electric field, which is voltage per meter. Using the voltmeter, you can measure the voltage. And you can measure magnetic field. Okay, Gauss meters are available. So these are all measurable entities. So to make this type of known waves, light and sound, acoustic wave, or the electromagnetic wave, so some entity is varying. Okay, so what we try to concentrate upon, okay, find something is varying. Who is that something? Okay, for a wave property of the matter. So then we try to focus on the issue that in a quantum mechanics class, we actually concentrate, I should say, about tiny electron moving. Okay, if suppose an object is moving. Okay, if an object is moving, can you see this object? You can see this object because it's a big object moving. So if I throw it, you can see how it is moving in the space. If I throw this, you can see how it is moving because it is observable. It's a large object. But basic question is that when I'm talking about the tiny electron moving around the nucleus, my problem is that I cannot see the electron. So just like the way I see a big object, I cannot do the same thing for this tiny microscopic electron. So here lies the clue of describing the wave nature. Because you cannot see the electron, so what do you do? But you know there is an electron. If I say, tell me where the electron, you can't be specific, but you know there is an electron. And that is all about atomic structure tells us. It is our limitation, it is our problem that I cannot see the electron. So what you do, you take chances to find out the electron, okay? Say you see the pictures, okay, the electrons are moving, okay? They are moving in orbital speed of the electron is close to the speed of the light, as you studied in the first question. So electron is moving. So at a given point, so therefore chance of finding the electron is varying every time. Just like this picture, okay, just like this picture, you can see something is changing. And okay, if I show it with some arrows, okay, arrowheads, you can see it. Say at this position, maybe I choose 2 points. Okay, at these 2 points, at these two given points, the chance of finding the electron, if I choose these 2 points, what is the chance of finding the electron at these two points? Okay, how do I calculate it? Okay, how do I get it? Okay, if I choose these 2 points, what you will notice at a given point, as indicated by those arrowheads, that the chance of finding the electron is always changing, always vary. Any change, any fluctuation, any variation makes a wave. So I am getting something wavy there. You can see in the picture also, but that wave is a wave of chances, chance of finding the electron. So the wave I am talking about in quantum mechanics courses is not the wave like sound and wave, electricity or electromagnetic wave. It is a wave of probabilities. It's a mathematical wave, chance of finding an object. So mind it, this is the clue of the classes. The wave nature of matter that we describe in a quantum mechanics course is basically the wave of probabilities, wave of chances, because chance in a mathematical language is called probability. This is popularly known also as the matter wave, as you know from your earlier courses. So these are few more illustration of the same story. Okay, so obviously those pictures you can see there, those curves, okay, they are not simple curves, they are basically representing the probability waves of the electron. Okay, now another wonderful issue is that you see, look at this picture. Okay, these are very good examples. See, I just show you again with some arrowheads. Okay, you see here, suppose I choose this point, okay, this point, this particular position, say this is a given point, maybe some x equal to 0. So at that position, so at this position, if I show here at this position, I wish to know what is the chance of finding the particle, chance of finding the electron. my problem key, my problem is that you see matter is moving. Okay, matter is moving every time. So because the matter is moving at that given, if I take suppose 100 photos, so 100 times I cannot see the electron. I cannot matter, that red ball you can see. So chance of finding the particle at that particular position indicated by the arrowhead is changing every time. So if it is changing, any fluctuation, any change makes a wave. So it's a wave of chances. I hope these pictures are so beautiful. Okay, you can illustrate. And mind it, I have kept so many pictures, A, B, C, D, E, F, G, H, or so many pictures are there. And the wave pattern is changing. Why changing? We'll address the situation. But you can see it is changing. Okay, you can see chances are varying. Okay, chances are changing. Okay, every time the chances are changing. Just a second. Okay, every time it is changing. Okay. So now, so it's a wave of chances. Okay, chances are all varying. Okay. Okay. So it is the probability is varying, chance is varying at a given point. Now you see it is becoming sometime plus, minus. You look at the curves. If these are almost our known curves, sinusoidal curve, etc., etc., etc. curves. These are some of the known curves of all of us. Okay. Now the idea is this: if these are some of the known curves, automatic and regular question that comes in business is this much. Okay. The next question that is coming in business is this much. Okay, fine. Okay, look at this ball again. It's a typical quantum mechanics problem. We'll solve it. Okay, there are 3 problems in your classes, in your course. Each problem will solve meticulously later on, but this is got a name also. These are very important for your examination purpose. But if you look at those problems, it's simply if you see a ball is simply moving. But if I use my interpretation, suppose it's a microscopic electron, my problem I cannot see it. So I take chance to find out the electrons. At a given point, the chance of finding the electron is changing and they are making waves. And you see it is becoming sometime plus, sometime it is minus, it is varying, it is changing. Sometime it is becoming positive, negative. And now automatic question comes in, can chance be negative? Can probability be negative? Suppose I am tossing a 1 rupee coin. So probability of falling head is half, probability of falling head is tail. I cannot say it's a chance of falling head is tail is negative. It is possible if it is a sole coin, but the chance of happening anything cannot be negative. Okay, but if you only simply interpret by the values of the that look at the curve, sometime becoming positive and negative. So we'll be in mathematical trouble if the function becomes negative because probability cannot be negative. So what we did at this juncture, we have taken the help of mathematicians. They told us that variable, you do not say probability, you just define this as just a function. So we call that function as wave function and indicated by some function psi. And you can see it is changing because the matter is moving, it is moving in space. So one of the variable is space, the position, the other variable is time because the nature of the problem might differ after some time, okay? Because ultimately this is a mechanics problem, the matter is moving. So they told us, mathematicians told us, okay, you just define that variable, the variable, and not just with probabilities. You say this has any function, say psi, and you see, you take square of psi, square modulus of psi to tell the probability, okay? And this is called the interpretation made by German scientist Max Born. If psi square is large, mod psi square is high, the object may be there. Objects mod psi square is less, object may not be there. I just show you some wonderful pictures, you'll realize, okay? Some more examples, you will realize, okay, so good. You see, look at the left-hand side graph, something plus, minus, okay, look at the graphs. Now you see, look at the graphs, the top picture, okay, indicated by those psi ones. So, okay, you see there, you see the curve may be positive and negative, but psi square is always positive. Okay, you can see there, it is always positive. Okay, so you see the variation. It can't be negative. So problem of minus sign is gone. So that's why we are relying on psi square because the psi square to know where the object is, because you know mechanics deals with basic question where the object is at a given point of time, WH question, where and when. So here also it's a mechanics problem, but mechanics of small particles. Because I cannot see the matter, I take chance to find out the matter. The chances are varying that I describe with some function psi, okay, wave function. And psi square, the mod psi square to be fair, is giving me the where the object is, probability of finding the object. Now one important, and you can understand object is there, so total probability has to be 1. Okay. Now, so that is another important idea because object is somewhere there. Okay, total probability of finding the object has to be 1. Okay, because it is somewhere there. The ball is moving. Now, another important issue is this. Okay, fine. Okay, if we look at this picture, okay, just suppose these are my size, these are my size square. But question is that, okay, because I presented this picture to you, I could say either this is, would get back to that ball problem. Okay, last the previous page, a ball is moving. Okay, if you get back to that problem of ball moving, okay, you see, because I presented that those curves to you, that's why I could say it is plus or minus. That's why I can say it is positive, negative. Because it is negative, you go for the chi square, not the chi to get the probability. But in real problem, a matter is moving. So who will, your job is to know where the electron is. That you have to know chi square, not chi square. But question is that unless and until you do not know chi, how do you get it? Job, suppose of any problem, any arbitrary problem, we'll be solving some problem very soon. Your job is to get the function psi. Okay, suppose I have got a electron moving. Okay, this is the electron moving. Okay, suppose I've got an electron moving around. Okay, you know electron is there. Chances are varying. All these studies I mentioned. Okay, but who will be giving the what the electron is? Psi square will give me. But before that, we need to get psi. Question is that who will give me psi? Now, to answer this question, we'll again, you see, one thing you try to realize what we have done. We have actually moved a lot from our old classical concept, where my technique was that if I've got an object, I will see the object, and if I throw it like this, my objective is that if I see the object, I can understand it is moving. Quantum mechanics problem is that this object is becoming from a very large object to I'm living in a very small object. Then that's why, because I cannot see, I went for probability interpretation. And that function variable I define as the function psi. So what I am doing, I am switching over to my discussion from the direct physical information to the mathematical information. I am using a function to represent the wavy nature of the matter. And psi square, all these studies you know. And that function I am trying to know. Now, automatic question, if I have to get psi, I have to again rely on my mathematics ideas. So idea is that how do you get functions in mathematics? How do you get functions in mathematics? You get functions in mathematics by solving differential equations. Okay, you have to solve some differential equations to get the function, any arbitrary function. Okay, so as for example, I have got any function f. Okay, how do you get it? Any function f of x or f of t or whatever it may be. Okay, how do you get it? My prescription is that I solve differential equation. Variety of orders of differential equation, you know. These are some of the first order equation. It will be second order equation. You know, if it is dy dt, it is first order. You understand it, okay? And if it is d2y dt2, it is second order. Okay, dqy dt3 means third order, like that. And all the powers are all one. Dy dt is not okay. Power is not like dy dt square. Okay, so it's a first degree equation. Okay, these are all mathematics idea. It's an old idea. You know them, so it's not a difficulty. My point is that you get functions by solving differential equations. I have to solve a differential equation to get the function. So question is that, okay, how do I get what is the differential equation? Who will give me the differential equation? Okay, now some person is there. Okay, don't worry. You have to take the help of a person to get it. So now let me do it more mathematical. Let me do it step by step so that you can understand in a better way. Okay, just a second, wait a bit. Okay, I'll be now presenting it, the details of the mathematical development. Okay, just wait for a few seconds. I hope you can see it properly. Wave function psi xt. Question is that it is just a mathematical function. It is just a mathematical function. Answer is that who will give me psi? Okay, how do I get the psi? Prescription is that because it is a mathematical function, solve a differential equation. Okay, because mathematics tells me that prescription is solve a differential equation. Okay, you solve a differential equation. Now, for example, I give you some examples so that you realize it. How you have already obtained some differential equations in your earlier. Suppose this is a very popular example. Suppose I have got a function fx. I want to get the function. So what do you do? These are some of the popular examples. Suppose d2x dx to fx equal to 0. I have to solve it. So you have done this much. You have taken a trial solution fx equal to a to the power mx. You have calculated dt of dx2. You have put the value of fx and solve it. This is a second order first degree differential equation. I'm introducing it because this concept will be needed. Okay, so mathematics idea is that to get a to get a function fx, the prescription is that you solve a differential equation. You solve a differential equation. Solve an equation. Okay, solve a differential prescription of the mathematicians with a differential equation which is going to give me the function psi. The function is this much. Okay, the equation is like this much. Okay, please see. This is the equation. Okay, this is the equation that is going to give me. That equation was proposed by an Austrian scientist, Erwin Schrödinger. Erwin Schrödinger proposed that equation. Erwin Schrödinger has proposed that equation. Erwin Schrödinger has proposed that equation. In 1926, he has proposed the equation. Now the equation looks like this much. This is the form of the equation: minus h cut square by 2m. Okay, d2 dx2. I'm using partial derivatives. Why I'm using, I'll tell you. Here, the meaning of minus h cut square, h cut is this one. The h cut stands for Planck constant by 2 pi. Okay, Planck constant is a constant, everybody knows it. And now m is the particle mass, mass of the moving particle. Okay, mass of the particle moving. For example, suppose I've got an electron moving. So the mass, and it is showing wave nature. So mass of this electron, okay, is given by m. So therefore m stands for electron mass in this case. Now next point is this much. If it is this, okay, plus Vx. Now Vx is called potential energy term. Vx is called potential energy term. Vx stands for potential energy. So that is nothing but my function psi Vx psi xt and ih cut del psi del xt. So I put it in a box. Now in this equation, you can realize here, you can see here, psi is a function of two variables. It's a two variable function. Psi is a function of space and also time. It's a two variable function. Because psi is a multivariable function, so my nature of derivatives are all partial. I am using partial differentiation because psi is a two variable function. So this is an equation of Schrödinger. Okay, and you can see this equation of Schrödinger. It's not a good looking equation that I cannot help you. It's the proposal of Schrödinger. And so if you look at this equation here, you can a few points to be answered. First question is that what is the, can anybody tell me what is the order of this equation? What is the order of this equation? What is the order of this equation? And next question is that what is the degree of this equation? Answer is that the order of the equation is that it's a second order equation. Second order equation because d2's are there. And what is the degree of the equation? Answer is that it's a first degree equation. Because the powers, all the powers, if you look at the powers of the derivatives, all the powers are 1. Okay, power is 1. So the idea is that the equation of Schrödinger, that is the basic equation of now of quantum mechanics. Okay, this equation is a second order, first degree partial differential equation. And if I solve it, what should I get? If I solve it, I am going to get the function psi. Now question is that can you solve this equation? I'll tell you that, but before I do so, I have to talk a bit more about something, some basic mechanics idea that you already have. Let me correct it with your old mechanics concept. So just give me a second more. So the if I use this old idea, I consider the journey of suppose I consider your old idea, one of your old concept, old example. That example I so often tell in your usual classes. Suppose I consider the journey of a car, moving car. Suppose at any time t1, the car is at any position x1. So this is x1. Suppose this is x direction. This is x equal to 0. So now, suppose the mass of the car is m. The car is moving with some velocity v along this arrowhead. So its momentum should be mass into velocity this much. So if you look at the description I've given here, mass, velocity, momentum, all these are basically the material property, mass, moment. So I'm thinking the car as a matter. So if I ask you a question, where the car would be at a given time t2, so you can easily answer my question by using this simple equation: force equal to mass into acceleration. Whose idea is this? Who has proposed this idea? Or in the differential form, you can write down this equation in this way. Now, what everybody knows it, you have solved this problem. Suppose some force F is equal to 10 Newton acting on the car, and let the mass of the car is 600 kg. Now I wish to know where the car is at given time t2, because I have been given a initial information that any time t1 it is at x1. So what I have to do, I have to on this equation in this way: d2a minus a. This is a very popular form of the equation to all of you. My objective is not to teach you that. My objective is, your only job is to put the value of f, put the value of m, integrate twice, you will get the position of the object at the given time t2. So you can easily do it. This technique you know, everybody studied it. My objective is to tell you that what is the speciality of this equation. What is the order of this equation? This equation is also a second order equation. And what is the degree of this equation? This degree of the equation, what is the degree of the equation? You see, powers are all 1. Powers are all 1. So this equation is also a first degree equation. So you see, whose equation is this? Whose equation? Who has proposed this equation? This is the Newtonian equation. Newton, this is nothing but Newton's second law. So idea is that if I've got a moving car problem, which is a classical mechanics problem, if I have to solve the problem, who will help me? Newton is going to help me. And the equation of Newton, essentially the second law of Newton, is a second order first degree differential equation. So idea is that if you have got a classical mechanics problem, large mechanics problem, big object problem, to describe the motion, describe the mechanics, whose idea you are using? You are using the Newtonian idea. And Newtonian idea basically deals with a basic equation, that is a second order first degree differential equation. On the contrary, the new idea is that you are getting in quantum mechanics idea, new quantum idea. The proposal of quantum mechanics is this. What quantum mechanics is telling you, the quantum mechanics tells you, if I've got here I am talking about a moving electron, okay, and showing wave nature. Wave nature is manifested by some function psi. So my first job, so physics is altogether different. Okay, why psi, etc., etc. I told you already. Now how? So now I'm trying to get psi. Who will give me psi? Use Schrödinger equation. That is the point I'm trying to tell you. So if you have to stay in a classical mechanics problem, Newton is going to help you. And if you have to stay in a quantum mechanics class, who is going to help you? Schrödinger is going to help you. Okay, and the structure of the Schrödinger equation I've just given you a few minutes back. It looks like this much. This is the basic structure of the Schrödinger equation. Okay, minus h cat square by 2m d2 dx2 of psi plus vx psi is equal to ih cat del t of psi. Psi is a two variable function of space and time. And what I told you, what is the order of this equation? It is a second order equation. What is the degree of the equation? What is the degree of this equation? The degree of the equation is also is a first degree equation. So now you try to realize, if you are dealing with a quantum mechanics problem, if you are dealing with quantum ideas where a electron is moving, and if you are dealing with a car problem, classical idea where a car is moving, both of them are mechanics problem because somebody is moving. But to describe car problem, who is going to help me? Newton is going to help me. And to describe electron problem, who is going to help me? Schrodinger is going to help me. And structurally, you see both the equations. The Newtonian equation is a second order first degree equation, and Schrodinger equation is also second order first degree equation. So mathematically speaking, both the equations have got the similar structure. Second, both of them are second order first degree differential equation. But basic physics is different. Classical mechanics, Newtonian mechanics deals on force, knowing the, classical mechanics have got some other version also, Lagrangian, Hamiltonian approach, I'm not getting into that. But the Newtonian idea, which you are mostly aware of, it deals on force with force calculation, so I need to know the big object, its mass, force, etc. And quantum mechanics deals with macroscopic object and probability interpretation, which is the basic variable is the wave function psi. So in a quantum mechanics problem, in classical mechanics problem, I try to get the force, mass, etc. and solve the problem. And in quantum mechanics problem, I try to get the, my first job is to get the function psi. So quantum way of thinking is to get psi by solving the equation of Schrodinger, and classical way is to solve Newtonian equation and describe the problem. And both the equations are structurally similar. So if you think, whatever may be your spectacle, maybe classical spectacle, maybe quantum spectacle, both of them are mechanics problem. But in classical physics, Newton is going to help me. In quantum mechanics, Schrodinger is going to help me. So classical mechanics problem begins with Newton, and quantum mechanics begins with Schrodinger. So any problem I have to do, my first job is to solve Schrodinger equation, get psi, and after psi, knowing psi, you can do many more things that we will discuss. So basic equation, somebody asked you what is the basic equation of classical physics? Newtonian equation. What is the basic equation of quantum mechanics? Schrodinger equation. Okay, and both of them are second order first degree differential equation. Now with all these things in mind, okay, let us again have a relook at the equation of Schrodinger. If you look at the equation of Schrodinger, obviously you understand by this time that in a problem I have to solve your function psi. I have to solve this equation and I have to get this function psi. Now, as everybody knows that in this expression h cut means Planck constant by 2 pi, m means the particle mass, m is the particle mass, and I is root over -1, as I mentioned a few minutes back. And here the term V stands for the potential energy. Now my next job is to tell you how the potential energy term, how this potential energy term is going to influence my problem. Okay, how it is going to influence our problem, how it is going to influence our problem. Okay, our problem, when we'll be solving problems, what would be going to be the role of the potential energy? Okay, how it is going to influence our problem. Now to illustrate that, I just go for the basic definition of potential energy. You know, suppose I have got a situation like this. Suppose I have got a this is x equal to 0, for example, and suppose this vertical direction stands for the x-axis. So if I keep a block here of any mass m, and suppose this length is x, so everybody knows the potential energy term V will be something like m into g into x. Now what is the meaning of the mg? Mg stands for the force. And what is the meaning of the x? X stands for the separation, or position, space. So if you can see that potential energy essentially is a function of position. V is a function of x. Now this corroborates with those ideas that you studied in electrostatic courses, like F is equal to minus dV dx. So if you integrate F over dx, then you get potential energy. Very similar concept. Now, so therefore it involves the quantities like force and the position. And idea is that if I keep it at a higher length, higher, suppose this I move it up. Okay, suppose uh, block is moved up. This is the new position of the block. The block is here at a higher length. Suppose it is at a higher value, say x1, which is greater than x. So if it is at a higher value, you can understand the x is going up, potential energy is also going up. In this force stands for the external force. Okay, it is the externally applied force, F external. Okay, here force stands for the externally applied force, F external. Okay, external force. Now, what is the external force here in this problem? In the case of this is the gravitational force. Forces due to gravity. Okay. Now this teaches this, but this is a known concept which everybody knows. But this is going to give you a wonderful idea. Idea is that because of this structure, suppose there is no gravity from tomorrow morning. If no gravity is there, what is going to suffer? This F external then will be zero. And how all of us will find? We'll find all of us are flying like this. So what is happen? We'll become free. If F external becomes zero, then the object or particle becomes a free body. And for a free body, you can see, look at this expression, the second term in this equation is going to be zero. So V becomes zero. So now this sends you a signal that in a given problem, if no external force is there, the body, I'm talking about a free body, and my potential energy term vanishes. So if I present it in a better way again, okay, you can see here, if I present it in a better way, it would be like this much. This is your original equation of Schrodinger, just to write down it quickly. Now, my concern is on psi, on this V, sorry. We want to know how V is influencing your problem. The answer is that V, the potential energy term, is like this much. It's a force, external force into space-time quantity. The idea is that if no external force is there, is V is going to be zero. If no external force is there, then that is the case of a free body. That is the case of a free body. Or if I consider a particle, that is the case of a free particle. For a free particle, therefore this term, this V term is going to vanish. This will become zero for a free particle. For F external equal to zero, that is the case of a free particle. On the contrary, suppose we are solving more realistic problem. Now this may be, suppose I've got an electron moving along this x direction. Along this x direction, I've got an electron moving. So for this electron, suppose no external force is acting, so its potential energy term will be zero. On the contrary, if I consider an electronic journey, suppose an electron moving around the nucleus, and you know electron will be under Coulombic forces. Okay, Coulomb force may be like this much. If it is plus Jd, Z is the atomic number, then a Coulomb force will act. Okay, Jd into minus C by 4 pi, suppose this is x direction, epsilon 0 x squared type of force will act. So the idea is that the force that is acting here, this force, this Coulombic force that on the electron, this is non-zero. So this force is it is a proportional to 1 by x squared type of force. Because in a given problem, Z is a constant, E is a constant, 4 is a constant, pi is a constant, and E epsilon is free space permittivity. So basically, this is non-zero. And if it is non-zero, then what you have to do using the usual idea, that F is equal to minus of dV dx, then you have to find out the corresponding potential energy. You have to get the potential energy, and that will be non-zero. Actually, if you calculate it, but the Coulombic potential is like this much. It is a 1 by x type potential. So what you have to do in that problem, if this is your electronic problem, now we have to put this value of V in the actual Schrodinger equation. So if I get back to the equation of Schrodinger, if pre-particle case V is 0, okay, but if I consider more realistic problem, when external force is non-zero, then obviously V will be equal to non-zero. So basically, if I consider a particle moving freely, no force is acting, my V term is going to suffer. It is going to be 0. So if you have to solve this equation of Schrodinger, your life becomes easier. If no V is there, if this is going to be 0, then you see the second term in this equation do not contribute. So your life becomes easy. But on the contrary, if F external is non-zero, which is like electron moving under Coulombic attraction, so then V is not, F is non-zero, V is non-zero. Then you have to put the value of non-zero V and solve the problem. So basically, the problem that you are solving, it actually depends on the how you see. If V is 0, your life is easy when you solve the differential equation. And if V is non-zero, then you have to, in a problem, you have to, depending on the problem, you have to find out the V and solve the problem. So that means if you are solving this electronic problem, this case, electronic problem moving freely along x-axis, no force is acting, V is 0. So my equation of Schrodinger equation is very easy because this term is 0. It's easy to solve. But on the contrary, more realistic problem, suppose I've got an electron is moving under Coulombic attraction. My F is non-zero, non-zero force. Okay, my V will be, as I calculated, my V is also non-zero. So I might have to put this non-zero V in the equation of Schrodinger. Okay, I have to put this non-zero V in the equation of Schrodinger and solve it. So idea is that V is actually going to vary from problem to problem. In a particular problem, you have to first know the potential energy term. Then you, if it is 0, I'm happy. My equation life is easy to solve the Schrodinger equation because ultimately I have to solve that equation to get the function. My job is to get the function psi. You should not forget that. Because psi is a function, I am solving a differential equation. Now differential equation solution becomes easier for a free particle because F0 V0, and but the most of the normal situation like electron under Coulombic attraction, which are the problems you have to solve. Suppose hydrogen atom problem. In hydrogen atom there is a nucleus and one electron is there. So there will be Coulombic attraction. If you have to describe the motion of the electron in the hydrogen atom, you have to use the Coulombic expression of the force. You have to get the potential energy. You have to put it in the equation of Schrodinger. Then you solve it. So then obviously your life will be more difficult because your mathematical travel will be more. So solution of the problem essentially depends on the value of V. So V is going to vary from problem to problem. But at least we can understand that we have to solve the problem. In my class, you have to solve the equation of Schrodinger. Schrodinger. You have to solve with the equation of Schrodinger. Otherwise, you cannot stay. Otherwise, you cannot do anything. So that is what we are trying to do. We'll try to get the solution of the equation. We'll solve problems later on, as I mentioned. So there we'll notice how V varies. But question is that can you solve this equation? Because it's a, if you look at the equation of the Schrodinger, okay, if I just write down the equation of the Schrodinger again, okay, if you look at the equation of the Schrodinger, okay, minus h cat square by 2m d2 dx2 of psi plus v is going to vary depending on the nature of the problem, I h cat del t of psi. Okay, so the question is that can you solve the equation? Because this equation is you see it's a partial differential equation. Partial differential equation. It is a partial differential equation. Right hand side is not equal to 0. So question is that how do I solve this equation? Do you know the technique of solving this equation? That is our next point of discussion, how to solve this equation. So what shall I do actually? We'll convert this equation into a very simple form. Very simple form. And because it's a solution or conversion of a differential equation in a simpler form, we have to use a technique of mathematics, that is a technique of solving partial differential equation, which is called separation of variable. Use separation of variable. Okay. Now, how you use separation of variable and convert this equation into a very simple equation, easy to solve equation, much like those equations you already know. Okay, so how do you do that? Okay, that discussion I shall make in the next class. So thanks for the time being. Tata, take care. We'll meet very soon.